Good morning, everyone. Let me start today's lecture with a Matlab example. The example I posted on Canvas is on quantization. So I want to show you two codes. One code is to beginning today's lecture, and hopefully I have time with another backup code to close today's lecture. So to begin with is a quantization. We did quantization many times before, and I give you one example is to do a audio signal, audio waveform. I hope you have tried that. Now, this is another quantization example code I post on the web. What it does is it works on the image. So first, let's see a clear order image, close all the variables. Then I read a picture. You can read BMP file, JPEG file, and different kinds of image file into Matlab and then process the data. So image read, the first one is Lena 1512 BMP. It's a Lena portrait, black and white picture. So first figure one is image show the original picture. Then what I did here, if you can see, let me read out to you. The picture is from the BMP file. Because it's black and white, so it's an array. Each element of the array of this image, the length and the width, each element of that pixel is an integer from 0 to 255. It is defined as unsigned integer of 8-bit, so 0 to 255. And then what I am doing here, I am using that. I did it here is to divide this number by 32. So I have 255 levels. I divide by 32. I have only 8 levels. Fixed is rounded towards 0. Actually, here everything is positive, so it's like a floor. So this, and then the temp, the variable, I multiply by 32 again, plus 15 is trying to span the entire range of 0 to 255. Therefore, it can plot out some great picture. So it only takes 8 values. In my case, it will be 15, 47, 79, 111, 143, 175, 208, 239. Of those 8 different levels to represent the value on each pixel. Figure 2 to plot this quantized picture. So let me do here, run it. Okay, so you can see here on the left, that is the original portrait. On the right is the quantized picture. Quantized picture, not too bad. Now I only using 8 different levels. In another word, I can use only 3 bits to represent the value of each pixel. Okay, and then it gives me a picture. Almost all the information of the original image is here. And then I loading another image. It's called the beta bear. That is a color image. So when you read the image, it will give you a tensor, dimension of the length, the width, and the 3. 3 is RGB, 3 different colors. Each element of that is a number between 0 to 255. Okay, so I do the same thing. I have here make this integer number to double and then divide by 64. When I divide by 64, 256 divided by 64, I only have 4 different levels, only 4 different levels. Then I'm doing a rounding towards 0. This is temp. And then I multiply by 64 just to make sure it's still, again, span almost the entire 0 to 255 in the range. Plus 31, make it in the middle. So I have 4 levels. You think of that, so from 0 to 255, and then I pick 4 levels. The first one starting from 31. Figure 4 to plot out this quantized image. Okay, figure 4, plot this quantized image. Let's see what we have. Okay, here we go. So this on the left is the original picture. Those are the 2 bears. And then on the right is this quantized image. Now remember, in this case, I only have 4 levels of each pixel of each of those RGB values. So I only need 2 bits to represent each color. And of course, in this case, because I have it's colored picture, so you will see a lot of details still there, even though I have do a much better job doing the quantization. Okay, you see almost every a big profile of these 2 pairs are here. Okay, so this is the very quickly that's the another example of quantization. It's working on an image as an you can think that as a function of space. It's an array of x and y. If it's RGB, you have x and y, and another dimension is 3 of those 3 colors. Okay. Now, here I'm going to continue with what we had last time on signal and systems, digital signal and digital systems. We have seen the importance of an impulse response. So what is an impulse response? It is a response of my system to an impulse function. We mentioned that last time because an impulse function, if you look into the frequency domain, that is just a span, it's just constant across all frequency range, across all the spectrum. So it gives me all the testing frequencies you excite the system with, and then you check the output. Of course, you know everything about the system. So once I got the response to an impulse, I know it in the entirety of the system. I can use that of Hn and working on any arbitrary input Xn and get the desired or the output, the actual output of Yn. How we relate Xn, Hn, and Yn, we are using a convolution. So let me just write on here. So here is Hn. So last time we talking about Hn is impulse response. So Yn, the output is equal to Hn convolved with Xn. And Hn is impulse response. So Hn is, my system is Hn. If the input is delta n, the output is the impulse response. All right. So we are using a convolution to represent the system. In practice, a system is a causal system. So usually a system is a causal system. And the system has a finite duration impulse response, which means this H, starting from H0, and you can have H1 go all the way to Hm minus 1 if the order of my system is m. So I have m non-zero values. Out of this range, it's causal. So H negative 1, this is 0. H negative 2, this is also 0. It's causal system. And beyond that, there are also zeros. So we have the finite here. The finite duration impulse response, FIR system, is here. Finite duration impulse response. On the other hand, if you have infinite duration impulse response, then suppose it's still causal. So you still have this k equal to 0 limit here, but on the other side, you don't have any limit. So it goes on all the way to infinity. That's the infinite IIR system, infinite duration impulse response system. Okay. And we also mentioned stability of a system. If the system is stable, we can also examine that on the impulse response. So what we have here is absolutely summable. Remember that, right? So we have this absolute summable. This is less than infinite. And k, if it's a causal system, it's from 0. Now, if it's IIR, go all the way to infinity. And now I want to make sure that is finite number. The sum is finite number. And it gives me a stable system. I have a question for you. Now, what about FIR system? according to this, is that safe for me to say any FIR system is a stable system? The answer is yes. Of course, any FIR system is a stable system because the H should be absolutely summable. Now, if FIR system, meaning that the summation only in the range k from 0 to n minus 1, so HK absolute value, right? It doesn't matter absolute value or it does not have that. Because I have only finite many of those H's, I have m H's, so it will always be less than infinity. So a finite impulse response system is always stable. Well, why don't we always choose finite impulse response systems? What are the good things about IIR systems? Later we will see. IIR system, actually, it gives us the benefit is that it will reduce the number of parameters. If you still remember, we had an example before that is on the accumulator, right? Accumulator, you're adding everything. You're adding, let me just flip back very quickly on that here. Remember that we have accumulator. Now accumulator, you can say this is a, if you are working with, in this case, I'm working with, these are the parameters, H0, H1, all the way is 1, 1, 1, 1. You actually have infinite many of those, right? If you're putting in one side. And I can do another way is yn equal to yn minus 1 plus xn. Now later we know if we have this feedback term, that actually gives us a IIR system. If you express that into this format, everything is on the x side, on the input side, then it has infinite many of impulse response because this is H0 equal to 1, H1 equal to 1, H2 equal to 1, continuous, infinite many. But IIR system, here I only have two parameters, where A is equal to 1, B is equal to 1, and I can do that. So the benefit is I reduce, sometimes dramatically reduce the number of coefficients. Later we will see when we're dealing with systems, differential equations and also differential equations, and also in the transformation domain, C domain. Okay, so these are the review on a digital system. Digital system is we are using the impulse response to represent a system. The premise of doing that, the condition that we can do that is based on that this digital system is a linear time invariant system. Okay, it's very important. It has to be a linear time invariant system because at that time we can use convolution. Right? Convolution mathematically is depending on the linearity plus time invariant properties. So it has to be a linear time invariant system. Okay, if it's not, sometimes we can do piecewise linear. We'll say, this small piece, it is linear. Sometimes we can do some approximation to approximate its linear system. So linear time invariant system is very important. Okay, so let's look at implementation of discrete time systems. For example, we are using a difference equation. Now this difference equation is first order. The order is we are looking at the y term. Now y has, this is the kind of feedback, the y has n minus 1 with 1 delay. We call that the first order. Similarly, if I have another term here, subtract a to y n minus 2 here, and then we call that a second order system. So it's the order is how many y's, how many delays of y's I have here. Okay, so we got this difference equation. Difference equation is very simple. It's first order. The input has two terms here, the current input and the previous input. And I put a weight B0, B1. Here I have a weight on the output, which on the delayed output, which is A1, conventionally we put a negative sign here because you can pull this to the left side of my equation. So yn plus A1 yn minus 1 equals to B0 xn plus B1 xn minus 1. So in general, you do that. Everything here on the left side is for y. And you can think I have A0 here as well. A0 is just by default is always 1 because I want yn here. And on the right-hand side, we have a sum of all these x inputs. Okay. So have that as an example. How to implement the system? How can we draw this in a block diagram and to understand the relation between input and output? Let's break them into smaller pieces. First, let's use a non-recursive system followed by a recursive system. So what I meant is here, I have an intermediate term called Vn. Vn is this part. Right? We have two of those input weighted, a sum of those weighted terms adding together give me Vn. So it's in intermediate term. This is a non-recursive that there is no feedback. I don't have a Vn minus 1 here on the right. So there's no feedback. It just everything is going forward from x input to output V. And then the second term, this one will follow by a recursive system. So Vn is Vn here. So you plug in your original equation, you got that. So yn equals to negative A1, yn minus 1 plus Vn. And because we have this term, I have another y here, that's output. So it's a feedback or it's recursive. I got my output, you stored in memory, you delayed one time unit, and then you put it into this equation again. So that is recursive system. So we can do that. It's very easy to see and very obvious. The second method is that I use a recursive system followed by a non-recursive system. So I do this first. Now, this time I only have one input. It's a very nice one input xn. Come into this first system, the intermediate result is wn. However, I got a feedback loop on that. wn delayed by one time unit, and then you add it. You actually put a weight of negative A1, then add it onto that. You got this equation. And then we have a non-recursive system, is that we take this intermediate level value of w, putting here wn, b0 plus b1 times w, and minus 1. And then you will get exactly the same output of yn. If you combine these two together, you will retrieve the original difference equation here. Now, can you prove that from here back to here? Okay. It's not that obvious. Okay. And maybe you need to do some calculations on the difference equation, but it's just not that obvious. I'm sure you can do it. Let me show you another way of prove that. The first part is very easy, right? This part is obvious, but the second part, let me prove it in another way. Let's look at how to implement this using block diagram. So the top picture A, is I have this xn coming in, go through a feed forward. So there's no feedback loop, right? Going this B0 times xn. Then I have a delay unit. Now this is a delay unit. Therefore, in this branch, I got a number xn minus 1. Why I'm using z to the power negative 1, later we will see in Z transform. This is exactly the effect in time domain, is that we have this delayed of one time unit. Weighted by B1, adding these two branches together, that gives me the intermediate value of Vn. And then I have a feedback loop. Vn coming here, give me Yn. With delayed unit, I have here Yn minus 1. It is weighted by negative A1 and then goes back here, feedback here. Okay, so that is the first implementation. That is the implementation here, this guy. And that will give me the system of the original difference equation. Now the second system is that I have xn coming in, okay? And I should be, the second part is this equation here. But let's see if those two are equivalent. Now from here to here, from these two pictures, A to B, what has changed? If you just look at the structure of that, all I did is, this is a feed, kind of a feed forward. And then I have a, let me go this, a backward feedback loop. So if you think this is as a block, now this feedback block is moving here, right? And then I have this feed forward is moving here, right here, okay? I just exchanged the order. Remember we said before, if the system is a linear system, well, indeed, each block, each small block like this, and the next one, each one of those is a linear operation. Therefore, I can swamp the order of those two, the blue circle and the red one, and that doesn't affect my system. So the blue one gets here, and of course the red one get there. Swamp the order, it does not change the system. Then we can, using the second figure, figure B, to check what is the difference equation to represent each one of those. And then we will get exactly the second equation here. Therefore, it will represent the same system. Okay, so that's my method of proving the previously why number 2 is also a valid implementation. So let's look at this picture. Now, since I swamped the order, so it will bring the parameter here. So this parameter is negative A1. And parameter here on this branch is B0. On this branch is B1. I just moved the exact same system from left to right, right to left. Right? And in this case, what I can do, I can combine the middle two delay units as one. So as one unit here, as one unit here. Because in this case, if you look at this branch, I have the same value, which is Wn, the same value, here. And the bottom is another value, which is a delayed value of Wn minus 1. So it doesn't change. I can just combine these two, remove one delay unit, and let that just have one branch coming through here. So in that sense, I can implement a system with reduced elements, physical element, I just using one delay. And indeed, picture C, the bottom picture, is exactly the same as the previous two, and it will give me the function, it will give me the system that fulfill the difference equation here, fulfill this difference equation right here. Okay. In general, we can have many parameters. We have many of those y's and x. In general, I have a y is k from 1 to n. The parameter is called a sub k. And then I have this feedback unit, yn minus k. And then the second term here, this is the input from input x, xn minus k, then k from 0 to m. Now, what's the order of this system? The order of this system is n, because n is here. N is of how many delayed feedbacks I have. In this case, the order is n. As I said, usually people like to move everything to the right, to the left with y's. So a sub k, y, and subtract k. And a k can, starting from 0 to n, and by default, we set A0 is 1. And this is equal to sum. Everything on the right is the input of x. So k from 0 to m, b sub k is x n subtract k. Okay. So this is the difference equation to describe all the linear time invariant system. In general, we are using that. And then to solve for this difference equation or to design a system, what we want to do is we want to find the parameters A case and a B case, okay, in order to make sure that the system will fulfill the requirement that we want. And from the previous analysis, we know we have two different structures. The direct form one structure looks like that. So we have a feed forward. A feed forward network give me an intermediate result of Vn. Then I use a feedback network here. So Vn is putting here. Then I have a feedback loop for all the y's. And putting those two together, it gives me exactly the same difference equation here. Using a block diagram, and what we have here is I got an xn as input, and we got this feed forward loop. So feed forward with all those delays coming back. So this point, I have xn minus 1. At this point of the branch, I have xn minus 2. And I have at this branch, I have xn minus capital M. And then you feed forward, adding together, give you intermediate result, Vn. Then the right is we got a feedback, so Yn. Then you feed back, you're coming back here. At this point is Yn minus 1. And all the way to here is Yn minus capital N. Now the length of these two may not be the same. One is, this ladder is length of N, this is length of N. So the length of that may not be the same. Actually, this is, I have n plus 1 here, and I got n plus 1 of those levels here. And then weighted feedback adding here and give me the output. So that's the block diagram, how we implement this system. Using the direct form 2 structure, we have a feedback loop first. This is feedback. So the input is very simple, just an xn, but we have this feedback loop give me an intermediate result of wn. Then I'm using a feed forward, all the wn's weighted with b sub case and give me an output yn. And those two forms, those two structures are exactly the same results. The block diagram show is here. So we have a block diagram, xn coming in. Now that is a feedback. So we got something you need to come back here, adding here, with weighted negative a1. And this intermediate result, wn, can go here. It's feed forward, connect here, keep feed forward with also a delayed version of wn minus 1, weighted by b1, and adding here, and so on and so forth. We said we can combine the middle delay units, so make there's only one delay unit for each level. And the length of left and the right, they are not the same. On the left, I have n minus n plus 1 levels. On the right, the feed forward, I have m plus 1 levels. So it may not be the same. But this is a block diagram that will implement exactly the same difference equation. Okay, so the last portion of this chapter is on correlation. Correlation of discrete time signals. Correlation, we have cross-correlation, we have autocorrelation. So correlation is trying to find the similarities between two signals. It's trying to find the similarities between two signals, x and y. And if it's autocorrelation, it wants to find a similarity between the signal and itself at a different time. So we have a different time. We have a lag of 0, no time difference, a lag of 1, -1, +2, -2, so on and so forth. So let's look at it in general. I have a cross correlation. Cross correlation of two sequences xn and yn. the cross correlation is represented by R sub xy of AL. AL is the time lag. So you can think of xn is a signal like this. Okay. If yn is another signal like this, I want to see how similar they are. But I'm going to, this is x, this is y. I'm going to shift y a little bit. Every time I shift it by one time unit, by one sample. And then I compare the similarity between these two. And then how much you shift, the L is the variable. L can take 0, positive, negative 1, positive, negative 2, and so on and so forth. The math expression is as follows. So R x y equal to the sum of xn times yn subtract L. L is the time lag. Is the difference, how you align those two signals together. And then we have the sum. Sum is in the index of time from negative infinity to infinity. L can take the value of any integer numbers. Okay. We change the variables. If you change variables n minus 1, you're using n prime to represent that, or n minus L. You're using n prime to represent that because n is from negative infinity to infinity. So you change this easily, n prime from negative infinity to infinity. And then you change to this format. Also, that's the same effect as the previous equation. That is x n plus L times y n. So the index L is the time shift, or we call that the lag, that how you align those two signals. Okay. So we have this equation here, and that's how we do the cross correlation. Again, L is how you align it. So let's say I have a signal x like this, y like this. So you're starting from this point, you multiply the value of on each time, right? And then you add them together. That's how you calculate the correlation with L equal to 0. And then you shift the y a little bit, to make it this starting from here. So this is L equal to 1. You do the same thing. You multiply all these points, this multiplied by this multiplied by this, piecewise multiplication, and then add them together. And you want to give that's the value of R. And if those two signals are very much the same, are similar, then you will have a large number when you do that. If they are different, because you average over a long period of time, the chances are you'll get a very small, close to 0 number. So in this case, now first let's look at, because of those two steps, the first one and the second one, we know that this cross correlation can be written in this way. So cross correlation of signal x and y of lag L equals to the cross correlation of signal y and x with lag negative L. You can think of those two, this is x, this is y. You just make x compare with y. So instead of shifting left, you have shifting right on the other direction. So it becomes negative L. And you can plug in here as well. You can see that that is from negative L to L, or the index from L to negative L. So we have that. With this summation, if we look at it closely, we find it very much like the convolution we had before, right? Do you remember what is the convolution of two signals? X, if I convolve this, x n y, how do you write it here? Y L minus n, right? And then here I have sum over n. And that will give me the convolution, let me call it C, convolution of L, right? N is from negative infinity to infinity. So this is kind of the discretized version of a convolution. The only difference here and there in the correlation is this guy here and here. So convolution is similar to correlation, cross correlation. The only difference is that I take the second signal doing a time reversal, n minus L, they change to L minus n. then that will be exactly the correlation. So indeed, I have it here. I have it here. So I take the first signal, convolved with a time reversal of second signal, and this convolution should give me the same result as I am doing a cross correlation between signal X and Y. All right. Autocorrelation. Autocorrelation of signal is you just change one X, the Y become one of the X. So it's a signal correlated with itself. So autocorrelation is R sub XX of L, and you put into this equation, you change the second term from Y to X, or change here from Y to X, then you get the autocorrelation. We have all these two properties here. So autocorrelation, in this case, autocorrelation RXXL equal to RXX negative L. Now, what does that mean? That means the autocorrelation is an even function, right? It's an even function of time L, time lag, and something look like that. This is my RXX. The second property is also true. So the autocorrelation is a convolution is my XL convolved with X negative L. Yeah, of course, because convolution, you can kind of take the second term, you're doing time reversal, you align with your self. So autocorrelation is the signal aligned with myself, and you just have a time shift or the lag. So let's look at, let me just try to make it easier. Let's look at a signal like this. This is my original signal X in, and I take myself, the signal, put it here, exactly line up here where L equal to 0. So I'm doing a correlation, every point multiply and get a result. And then I can shift it here by 1. This is L equal to 1. So you do the same thing. This point multiplied by this point multiplied by this point. And of course, the origin of this point multiplied by here now is a 0. This point by, and then you add them together. That gives you a autocorrelation value of L equal to 1. Okay. That's how we do autocorrelation. Now, if we do that, we know that the maximum value we can get is when the lag equal to 0. Because when the lag equal to 0, what we have here is we align the signal perfectly with itself. So we will have here is the energy of the signal, right? From the previous picture, you take this point, multiply by this point. What do we have? We have instantaneous power here, and this point multiplied by this instantaneous power, and you're just adding everything together. You got the energy of the signal. That's the best, that's the maximum you can get. If you off a little bit, it will always get you a smaller number. So we got that. The autocorrelation will always be less than or equal to the energy of the signal when the lag L equal to 0. The same thing is true for cross correlation. Actually, we can prove in that way. You can just multiply by this one, and then you can prove it easily. So the cross correlation is that it will always smaller or equal to square root of this Rx0 times Ryy0, which is square root of the energy of first signal times the energy of the second signal. And the cross correlation will always be smaller than that. Using these two inequality, we define the normalized autocorrelation and the normalized cross correlation. Normalized is just that we have this autocorrelation divided by the maximum value it can take, which is the energy of the signal. And we have this is also correlation, autocorrelation, but it's normalized, such that the absolute value of that is less than or equal to 1. We normalize that. So when I check with the autocorrelation, I can check with this value, the normalized autocorrelation, because it's bounded in -1 and 1. Now we know if my value of this row becomes 1, then I know the autocorrelation at this point of lag L is maximized. Now, if it's equal to -1, I know this autocorrelation, when I have a lag of L, it's exactly the opposite of myself. So it's going to give me -1. And it's always in between -1 and 1. A normalized cross-correlation, same definition, similar definition. We have a rho xy, and that is my cross-correlation R xy of lag L, divided by square root of energy of first signal, energy of second signal. And then we also have this rho xy of L is bounded between -1 and 1. If xy are exactly the same when with a lag of L, then it's equal to 1. When xy with a lag of L is completely different, it's completely random, they're different. And then we will get a very small number, is 0, close to 0. That's when those two signals doesn't have any pattern that are similar. So we have the cross correlation here and autocorrelation with periodic signals. So we have here, if I have a periodic signal, in that case, I only need to look into one window from 0 to n-1. Suppose n is the period, So periodic signal, I only need to look into one of those windows and get this number divided by n. That's my cross correlation. Similarly, I have autocorrelation. Is that we take an autocorrelation, but I only take one window n from 0 to n-1. Okay, let me shift to the Matlab. This Matlab example is also shared on Canvas. Let me just read out to you if it's too small. So what I did here is I have n is a time index from 0 to 100. X is a signal, that's 0.5 to the power of n. So it's because the base is 0.5, so it's decreasing all the way from 1. It decreases. I just want to show the shape of the signal. And then what I have here is that I have a correlation, X correlation of X and Y. Y is a signal itself, but Y is I am taking X, doing a circular shift. So X is a signal look like this. Y is I'm doing a circular shift. So it's starting from here, but it ended with here. So it's a circular shift. So from this point to this point, that is Y. So it's a little different with a lag of 5. Those two signals is 5. Then I do a cross correlation of X and Y, and find the value of R, which you see here, and the lags. Lag is this is the lag for correlation. Now, if you align here with that, this lag is 0, and then move. So for figure 1, I want to plot out what does the signal look like. And then on figure 2, what I did is I generate two random sequence, W1 and W2. They are all Gaussian random number with length 100. Doing same thing, correlation, W1, W2. Figure 2 will show us. So here is figure 1 on the left. Figure 1, remember that's X, and X itself has a circular shift. So we have here, we got when the signal aligned, actually when the time lag is equal to 5. So you shift, and that gives me the correlation with the strongest. When it's off, then I will have a very small number, and eventually it deteriorates almost to 0. So the figure 1 on the left is the correlation of signal X and Y. Now figure 2 is the correlation between signal W1 and W2. Now because they are random variables, so what I have here, everything is random. This is my R of lag of L. It's random. I don't see anything here. If you take long enough, adding them together, the effect will be close to 0. I don't have any correlation between these two random variables, W1 and W2, random sequences. Okay. Then I continue with that. Now I generate a random variable called W1. I'm doing a cross correlation W1 and W1. So figure 3, I'm actually showing you the the autocorrelation of this random Gaussian random variable, random sequence, cross correlation. And then figure 4, instead of using the Matlab X-Cross to calculate the cross correlation, I'm just doing a convolution. So figure 5, plot a convolution between W1 and the inverse of W1. So this is W1 from the last element and step size -1 back to 1. So I'm doing a time reversal of W1, right? So these two pictures, 3 and 4, they should give me the same result. Let's try that. Okay. On the left, that's figure number 3. Indeed, I have a autocorrelation because of random variable. So the largest I have here is when the lag is equal to 0 in the middle. That gives me the energy of this random sequence W1. All the rest, it should be zeroed. If you take long enough, let's say this random variable has 10 million of those points instead of 100, and then you will smooth them out. It gives you a one energy in the middle, and then across the other of this legs, they are all zeros, autocorrelation. And on the right, this picture is the same. That's just I'm doing the convolution, and it shows me exactly the same result. So I got a peak when the lag equal to 0. So that is remember the white Gaussian noise we said last time. When I do the frequency spectrum, it gives me a constant of all frequencies, right? Now, if I'm showing the autocorrelation of a white noise meaning that on those two samples, W1 at time 0, W1 at time 1, they are random variables, but they have not correlated at all. So each one is kind of pick up a random number by itself. So they have no correlation whatsoever across time. Therefore, the autocorrelation function looks like that.